Welcome to the deep dive. So, following our chats about, Boyajian's star and Dyson spheres, today we're tackling something, well, huge.
Uh-huh.
This core question in the search for alien life. If the universe is just so vast, teeming with possibilities, then where is everybody?
Yeah, the Fermi Paradox. Enrico Fermi, wasn't it? 1950.
That's the one, also called the Great Silence. It's a real head scratcher.
It really is. It sounds simple, but wow, it drags you into some deep waters about, life, intelligence, our whole place in the cosmos.
Exactly. It challenges the whole idea that life and intelligence just naturally pop up, doesn't it?
It forces you to really examine those assumptions.
Okay, so maybe we should start with something basic, but surprisingly trippy. What is life?
Huh, yeah, easy question, right? We all think we know it, but defining it, that's tough.
Biologists have their checklist, don't they? Metabolism, growth.
Right, your standard textbook stuff. Adapting, reproducing, responding to things, the usual signs.
But NASA goes a bit broader for astrobiology. They talk about a self-sustaining chemical system capable of Darwinian evolution.
Which makes sense if you're looking for life that might be fundamentally different from ours. It's about the process, the evolution part.
Right, that ability to change and adapt over generations through natural selection.
Exactly. And look, even without one perfect definition, we kind of have an intuitive feel, right?
Yeah.
It's enough to let the search actually happen. We know roughly what to look for, or at least what kind of weirdness might signal it.
Okay, so let's ground this back on Earth for a sec. Our own origin of life. It's this amazing mix of chemistry, geology, biology.
Totally intertwined. And fundamentally, it seems to need carbon and water, at least as far as we know.
And the building blocks, these complex organic molecules, they're actually not that rare, are they? We find them elsewhere.
That's the fascinating bit. Amino acids, things like that. We see them in meteorites, comets, even floating in interstellar gas clouds. The ingredients seem to be, well, everywhere.
So the ingredients are common.
Yeah. The real mystery is how they went from just being there to assembling themselves
Mm.
into something that lives and replicates. That's the jump.
And we have ideas about where that jump might have happened, like those deep sea vents.
Hydrothermal vents are a big candidate, yeah.
Yeah.
All that chemical energy pouring out, or maybe extremophiles, those microbes that live in boiling water or acid or whatever. Maybe they show us how life can start in really harsh places.
It's just incredible to think about. And the timescales involved are just vast.
Right, universe, about 13.7 billion years old.
Our solar system, maybe 4.5 billion.
And the first hints of life on Earth, maybe 3.5 billion years ago, give or take.
And us, modern humans, like 300,000 years.
A blink. Seriously, a cosmic eye blink. And remember, our sun isn't even ancient. Loads of stars are billions of years older.
Which means planets around those stars could have had a huge head start. Billions of years, more time for life to get going, maybe even become intelligent.
Precisely. That's central to the paradox.
Okay, so scientists talk about these like 5 major stages for how non-living stuff could become life. Can you walk us through that general idea?
Sure. So step one, you need the basic building blocks, amino acids, nucleotides forming from simpler inorganic stuff.
Okay, got it.
Then step two, these blocks need to somehow organize themselves into more complex things like proteins or RNA, self-assembly.
Right.
Step three, you need the first chemical reaction pathways, metabolism basically, ways to process energy.
Makes sense.
Then four, these bigger molecules somehow clump together into larger structures, maybe get enclosed in a membrane, like a protocell.
Okay.
And finally, the big one, step five.
Yeah.
It becomes a self-sustaining system, something that can maintain itself and evolve. Darwinian evolution kicks in.
Wow. Each step sounds incredibly unlikely on its own. Put them together.
It does seem improbable, doesn't it? It reminds me of that Fred Hoyle line.
Oh, the junkyard tornado.
Exactly.
Yeah.
The chance of life arising spontaneously is like a tornado whipping through a junkyard and perfectly assembling a Boeing 747.
Yeah, it highlights the sheer, maybe astronomical unlikeliness of it just happening by chance.
Which, leads us back to wondering where else, even nearby, might have some potential, even if it didn't make the full jump. Where else in our solar system?
Well, the moon and Mercury are probably out, right? No liquid water to speak of.
Pretty much, yeah. Too dry, too exposed.
But Venus and Mars, they're more interesting cases. Past potential.
Definitely. We see strong evidence both had liquid water on their surfaces way back, billions of years ago.
Mm-hmm.
So early on, maybe, they could have been habitable.
Before Venus turned into, well, hell, and Mars dried up and lost most of its atmosphere.
Right. Their current surfaces are pretty nasty.
But then you have the outer solar system, those icy moons. Europa, Ganymede, and Enceladus.
Titan, Callisto, Triton 2. Yeah, these are super exciting. The big draw is the potential for huge oceans of liquid water under the ice shells.
Hidden oceans protected from space.
Exactly. And maybe, just maybe, there are hydrothermal vents down there on their ocean floors, just like on Earth.
Which could provide energy and chemistry for life. Whole ecosystems, totally separate from Earth.
That's the hope. And that's why there are serious plans for missions to go sniff around these moons, looking for biosignatures, signs of life.
Speaking of biosignatures, that takes us beyond our solar system to exoplanets. How do we even look for life signs light years away? Spectroscopy.
That's the main tool, yeah. We analyze the light from the star that passes through the exoplanet's atmosphere, or light reflected off it.
Looking for fingerprints of different molecules?
Exactly, spectral features.
Hmm.
We assume life, if it's out there, might be kind of like us, carbon and water-based, so it might change its atmosphere in detectable ways.
Like putting gases in there that wouldn't normally be there?
Precisely. We look for things like oxygen O2, ozone O3, methane CH4, water vapor H2O.
And isn't the combination of oxygen and methane supposed to be a really strong hint?
Oh yeah, that's considered a potential jackpot.
Yeah.
Because oxygen and methane react with each other. They destroy each other chemically.
So they shouldn't really exist together in large amounts for long.
Unless something is constantly pumping them out. And that something could very well be life. Biology.
A big chemical imbalance pointing towards life.
That's the idea.
Yeah.
It's a major driver for designing future telescopes. Missions like the old Darwin or terrestrial planet finder concepts were all about looking for those specific gases, especially in the infrared.
Those specific missions didn't happen, but the goal remains.
Absolutely. The science is pushing forward, looking for ways to detect these faint signals from distant worlds.
Okay, so shifting gears a bit. If we're thinking about intelligent life, communicative civilizations, there's the Drake equation. Frank Drake, 1961.
Ah yes, the famous equation. N-RSF FEP NEFTEFL. Looks impressive.
But it's less about getting a precise number n and more a way to organize our ignorance, right? A framework.
That's a perfect way to put it. It breaks the big question, how many civilizations are out there right now, into smaller pieces.
Like the rate of star formation, fraction of stars with planets.
Right. RSF is star formation rate. FP, fraction with planets. Now, number of habitable planets per system. Those first few we're actually getting better data on thanks to exoplanet discoveries.
Okay, but then it gets fuzzier.
Way fuzzier.
Yeah.
FL, the fraction where life actually starts. Phi, the fraction of that life that becomes intelligent. FVC, the fraction that develops communication technology we could detect. And FL, how long those civilizations stick around, broadcasting or just existing technologically.
And those later terms, FL, Phi, FCL, they're basically huge unknowns, aren't they?
Pretty much educated guesses at best. Wild speculation at worst. That's why you can plug numbers into the Drake equation and get answers ranging from millions of civilizations in the galaxy.
So just one, us.
Exactly. It really highlights how much we still don't know about the probability of life and intelligence evolving, and especially about the longevity of, well, it's trying a different approach. Instead of estimating probabilities, let's just listen. The core idea of SETI is, if Earth-like conditions made us, maybe similar conditions elsewhere did too.
And they might be making noise we can detect. Radio waves, mostly.
That's been the main focus, yeah. Either deliberate beacons, like Hello Universe, or maybe just accidental leakage from their own technologies, like our TV and radar signals. Sensitive radio telescopes could potentially pick that up across light years.
And there have been lots of searches over the years, all sky surveys, targeted searches like Project Phoenix.
The Allen Telescope Array, the big Breakthrough Listen project now, lots of effort, scanning the skies.
It's not just radio, though, is it?
Yep.
Some look for lasers, optical SETI.
Correct. Looking for really short, powerful pulses of laser light. The thinking is maybe advanced civilizations use lasers for high-bandwidth interstellar communication. A brief, bright flash.
So listening for signals, but what about looking for artifacts, evidence of alien engineering, technosignatures?
Yeah, that's another angle. Looking for weird stuff that doesn't seem natural. Like that interstellar object, Oumuamua, its shape and movement were odd.
Or Boyajian star with its strange dimming.
Exactly. Or even searching for hypothetical megastructures, like Dyson spheres, which we talked about before. Huge constructions that might portray a super advanced presence.
But we have to be careful with these anomalies, right? There have been false alarms.
Oh, definitely. The discovery of pulsars initially caused a stir. Those regular pulses looked artificial for a moment. They were even nicknamed LGM-1 for little green men.
Right. And the wow. Signal in 77, that famous unexplained radio burst.
Still unexplained. A strong signal. Looked artificial in some ways, but it was never detected again. So yeah, extraordinary claims need extraordinary evidence.
And so far, nothing definitive.
Nothing unambiguous. Which swings the pendulum back to, okay, maybe there's something really special about Earth. What made it possible for us to be here?
And the list of factors is, well, it's long. It feels like we won the cosmic lottery.
It kind of does. First off, our sun. It's relatively stable, not too big, not too small. Crucially, no regular superflares that would just fry everything.
In our orbit, the Goldilocks zone. Right. Just the right distance for liquid water on the surface.
And not just now, but for billions of years, the continuously habitable zone. That long-term stability is key.
That's Earth's mass. It's big enough to hold on to an atmosphere.
But not so big it became a gas giant. And it's massive enough for plate tectonics.
Which most people think of for earthquakes and volcanoes, but it does more, right? Regulates climate.
Hugely important for regulating CO2 levels over geological time, which helps keep the temperature stable. It's a planetary thermostat, basically.
Wow. Okay. What else? Our atmosphere itself?
Yeah, formed from volcanic outgassing, maybe some captured from the early solar nebula.
Yeah.
And our water likely delivered by comets and asteroids early on. Enough for oceans, but not so much water that we're a total water world with no continents.
We've also been relatively lucky with giant asteroid impacts recently, haven't we?
Compared to the early solar system, yes. And our large moon, probably formed from a giant impact.
Yeah. What does the moon do for us?
It stabilizes Earth's axial tilt. Without it, our axis might wobble chaotically, leading to extreme climate swings, so more stable seasons, more stable climate.
And Jupiter. Does it help?
Probably.
Hmm.
Its huge gravity likely acts as a sort of cosmic vacuum cleaner, deflecting or absorbing many comets and asteroids that might otherwise hit Earth.
Okay, so stable sun, right distance, right mass, plate tectonics, atmosphere, water, big moon, giant neighbor. Anything else?
Well, no nearby supernovae going off recently which could sterilize the planet with radiation. And even the metallicity, the amount of heavier elements in our solar system, seems to be in a sweet spot for forming rocky planets like Earth.
It really is an incredible list of fortunate circumstances.
It seems that way, yeah. A remarkable confluence.
Which brings us right back, full circle, to the Fermi Paradox. If all this was needed, maybe it's super rare. Yeah. But given the sheer number of stars, galaxies, potentially habitable planets.
And the age. Many stars much older than the sun. Planets with billions of years head start.
And the idea that interstellar travel, while hard, might not be impossible on long timescales. You'd think someone would have spread out, left signs.
Exactly. If civilizations arise and last, even if travel is slow, the galaxy could potentially be colonized, or at least explored in, say, tens of millions of years, which is short compared to the galaxy's age.
So the probabilities seem to say someone should be out there, maybe everywhere.
That's the calculation, yes, based on scale and time.
But the observation is silence. Nothing. No confirmed signals, no probes, no visits we can verify.
That's the paradox. The apparent contradiction between high probability estimates and the utter lack of evidence. The great silence.
So how do people try to resolve this? What are the main ideas floating around?
Well, one big category is simply, maybe they don't exist, or they're incredibly rare. The rare Earth hypothesis.
The idea that while simple life might be common, getting to complex, intelligent life requires that whole long list of lucky breaks we just talked about. Maybe Earth is truly unique, or close to it.
That's the core of it. Maybe some bottleneck, the jump to multicellular life, or intelligence, or technology is just fantastically improbable.
A humbling thought, that we might actually be alone, or practically alone.
It is. But there are other possibilities, right? Reasons we might not see them, even if they do exist.
Yeah, what about those?
Well, maybe interstellar travel is effectively impossible, or just not worth the immense cost and difficulty for any sane civilization. Physical limits.
Or maybe it's sociological. They choose not to travel or communicate. The zoo hypothesis idea, where they watch us but don't interfere. Or maybe they're just fundamentally different, uninterested in expansion.
That's a whole category of speculation. Or a darker thought. Maybe technological civilizations just don't last very long.
They self-destruct. Nuclear war, climate change, runaway AI, something like that.
Yeah, the great filter might be ahead of us, not behind us. Maybe advanced societies inevitably hit a wall, natural or self-inflicted. So they flicker into existence and then vanish before they can spread far.
That's sobering. Or maybe it's just timing. We only just got radio telescopes. Maybe signals are on their way but haven't reached us yet.
That's possible too. Cosmic distances are vast. Or maybe we are one of the first. It seems unlikely given the older stars, but it's a possibility.
And then there's the fringe stuff, like they have visited, but it's covered up, or we didn't recognize it.
Those ideas are harder to test scientifically, but they're part of the conversation too.
So, wrapping this up, it feels like we're left exactly where we started, in a way, this huge question mark.
Pretty much, the Fermi Paradox, where is everybody? It remains one of the biggest, most profound, unanswered questions out there. We just don't know the answer.
It spans this incredible range, from us being totally unique and alone in the galaxy.
All the way to the possibility that the galaxy is teeming. But there are reasons we haven't seen them yet, or reasons they don't last long.
Yeah, the great silence holds its secrets tightly.
It really does. The tension is still there.
Hmm.
The numbers suggest life should be common. The observations suggest it's not, or at least it's not obvious.
And thinking about why it's silent, it really does make you reflect on our own civilization, doesn't it? Our own future.
Absolutely. If we could figure out the reason for the silence, it might tell us a lot about our own long-term chances. Are there natural limits we'll hit? Are there dangers inherent in advanced technology that everyone succumbs to?
Yeah. Understanding the paradox might be key to understanding our own potential trajectory, whether we're destined for the stars or something else.
It's a powerful thought motivator, that's for sure.
So, for you listening, as we end this deep dive, which answer to the Fermi paradox resonates most with you? Do you think we're rare? Do you think they're hiding? Or do you think there's some great filter out there? What does your gut feeling tell you about our place, our solitude, or lack thereof, in this immense silent cosmos?
It's definitely something to ponder.